Hello class and welcome to today's class. We will continue with the stage 4, machines and application of the laws and principles of motion. And now we're going to go into the subtopic 4.2, the lever, la palanca, part 1. So let's go into it. Okay, what is the objective for this class? We want to understand what a lever is and to get to know the three classes of levers there are. And number 2, the second objective, is to solve some problems involving first class levers. You will understand in a moment what a first class lever is. So what is a lever? The definition of a lever is extremely simple. It's this. A lever is a rigid bar with a support called fulcrum. Okay? This is your bar and this is your fulcrum. That's all you have to understand about a lever. It's just these two pieces. It doesn't get any simpler. So just remember this word, fulcrum, fulcrum. It's just a fancy word for support. And that's what a lever is. Now, how does it work? Let me explain to you. Okay, let's draw the ground, a fulcrum, and a rigid bar. There you have it. Okay, so this is a lever, right? Because we have the fulcrum and the rigid bar. Okay, so how does a lever work? How do we use it? In this way, what we do usually with a lever is we place a load on one extreme, okay, which is basically a weight. A load is a weight. So this is the load. And since it's a weight, it's measured in newtons, right? It's gotta be a force. Okay. And we want to raise this load by applying a force on the other extreme of the lever, which we will call effort. Okay, this is the input force that you're applying on the device. But in the specific case of the lever, this is called the effort. Okay, so this is a force. Effort, whenever you see this letter, that means effort, and that means the force that you're applying to raise the load, which is another force in the form of weight. Okay, so that's basically what we do with a lever. I mean, it doesn't get any simpler, right? We have a load, which is a weight, and we apply an effort on the other extreme in order to raise that load. But there are other two quantities of interest regarding the lever, and these quantities are the following. The distance from the fulcrum to the load is called the load arm. So this is known as the load arm, el brazo de carga. And the distance from the fulcrum to the effort, as you may guess, is called the effort arm. So these two things, load arm and effort arm, are distances. The distances from the fulcrum to the respective load and effort on your lever. And that's how the lever works, and that's what the basic parts or characteristics of a lever are. These four things: load arm, and effort, and fulcrum. Let me put it here. Okay, let's continue. So what are some examples of levers in daily life? For example, we have the seesaw, the scissors, the wheelbarrow, and the tweezers, and the prongs, which are those things with which we pick the carne asada and stuff like that, right? And so let me, for example, for each of these, I'm gonna spot the fulcrum for you. Okay, these are levers. So if they are levers, they should have fulcrums, and those fulcrums are the points that are fixed when you use the lever. So for the seesaw, the fulcrum is this, right? Because this is the place or the point that remains fixed while the bar goes up and down. With the scissors, the fulcrum is this part because this is the part that remains fixed when you handle it, okay, applying your effort here, and the load will be applied over here in order to cut some paper or something. Okay, the wheelbarrow, where is the fulcrum? Right here. What when you raise, for example, when you raise the these handles, when you lift them, if you can imagine, the place that's going to remain more or less fixed is this little part here. Okay, the point of contact of the wheel with the ground. So this is the fulcrum. Okay, and here's where your effort goes, and this is where the load goes, which is the cement and the sand and all that stuff. For the tweezers, what do you think is the fulcrum? The part that remains fixed when you use this thing. It's this part, right? This is the fulcrum. This is where you apply your effort, and this is where the load comes out. Okay, so those are some examples of levers in daily life, and all of them have an effort, a fulcrum, and a load. Okay, so I'm going to tell you about the three classes of levers that exist. The first class is this one. Is when you have a lever with this configuration. Exactly, this configuration exactly. First, the effort. Okay, as you can see, we have this person which is applying an effort on this part of the lever. Okay, let me go to another color. So we have effort on this part of the lever, and then we have the fulcrum, which is this little block in here. This is the fulcrum, and then the load. So if you can see, we have the configuration effort, fulcrum, load. When we have that configuration, effort, fulcrum, load, we call this type of lever a first class lever. Second class lever, the configuration is effort. For example, in a wheelbarrow, the effort is right here in the handles, right? This is where you put your effort. And then we have the load, which in this case is here, all the cement and the sand and the rocks, like I said before. And then we have the fulcrum, which is this little part over here. So the configuration effort, load, fulcrum is known as a second class lever. And finally, we have the third class lever, whose configuration is this: fulcrum, as you can see here in the tweezers. This is the fulcrum, and then the effort over here. This is where you apply your effort. This is where your fingers go, and then the load, which is over here. Okay, so fulcrum, effort, load classifies this lever as a third class lever. So as you can see, the differences between all of these classes of levers is only the order of those three things: fulcrum, effort, and load. If you have different orders, you will have different classes. So how do we memorize which configuration goes with which class? There's a very simple trick and very clever. It's not so clever. It's actually simple to come up with. Okay, so this is the mnemonics to memorize the classes. Mnemonics is a word to describe all those techniques that allow you to memorize something. For example, remember, you're taking mathematics 2 right now, and when you want to memorize the trigonometric functions, you use the word SOHCAHTOA. Remember that? Or you use the phrase coca con hielos. And I've seen many other examples. Those things are examples of mnemonics techniques. So it's stuff that allows you to memorize something that otherwise you would not be able to memorize. So in order to memorize the classes, we have the following mnemonics. Imagine an elf whose name is Ethel. This elf is Ethel. And all you have to do to memorize the classes is memorize this phrase. Ethel is an elf that fell down. Ethel is an elf that fell down. Okay, how does this help me memorize the classes? Very simply, look at this, at the name of the elf, Ethel. This is the first class, okay? Because the first class has the effort first, the fulcrum second, and the load at the end. So this is the first class. You see, it's an elf, and this is the second class. Because the second class has the effort first, and then the load, and finally the fulcrum. You see? And we continue. It's an elf that fell, and this is the third class. Because the third class has the fulcrum first, and then the effort, and then the load. Okay? So that's how you can, if you, that's how you can memorize the classes with, by memorizing this simple phrase. If you memorize it, which is very simple, you can come up with the classes without any effort at all. That was a pun. That was a good pun. Okay. Okay. Now let's go into the fundamental equation of the lever. What rule or what principle governs the functioning of a lever? It's this: the effort times the effort arm equals the load times the load arm. So again, it's a good idea to memorize this equation. It's not complicated. You can, by following the same idea as before, you can think of this as ella, you know, kind of like that, ella, and that word can help you memorize this equation. And we're gonna use it right now. Okay, so I'm going to give you three examples of solutions of problems that involve a first class lever. I want you to have pencil and paper by your side and your calculator because we're going to do these examples in real time. Okay, I'm going to go slowly but not too slow, okay? So get ready and write quickly. Okay. Don't write the problem. Just follow me and do the operations on paper. So let's read. How much effort is it necessary to lift a rock of 200 newtons? This is going to be the load of weight if such rock is placed 0.5 meters from the fulcrum of a first class lever of 5 meters. So let's draw the whole thing, okay? Always draw, always draw. That's a very good technique in physics or mathematics or anything. Always draw. If you can, draw. So let's draw the lever. We have the fulcrum. We have the bar. Let's place the rock over here. And that's it, right? Okay, so how long is the lever? The lever is 5 meters long. So all of this is 5 meters. And we are told that the rock is placed 0.5 meters from the fulcrum. So this distance over here is 0.5 meters. Okay, fine. So we have everything drawn in order to solve the problem. So here I'm going to collect my data in this part. So we have the load. Remember, the load is the weight of the object that you're trying to raise. So it's 200 newtons, okay? Now we also have the load arm, which is the distance from the fulcrum to the load, as I said before. So this is 0.5 meters. Okay? Now, question, can we get the effort arm? Because we are not told specifically, that is, the effort arm. But with this information, we can get it, right? Because the effort arm is, by definition, the distance that goes from the fulcrum to the effort. And remember that the effort is applied at this point. So it's this distance. How can I find this distance? Very simply, we have that the whole lever is 5 meters, and this little bit is 0.5 meters. So clearly, this other part will measure 4.5 meters, and that's going to be the effort arm. So let's write it down. So I have three three pieces of information, and I'm being asked to get the effort. So how can I find the effort? Very quick, very simply. I resort to my fundamental equation for levers. Effort times the effort arm equals the load times the load arm, ella. I mean, if you want to memorize that word, do it. If you don't, don't. I think it sounds corny. Okay, so let's substitute all the information in here. So the effort is the thing that we don't know. The effort arm is 4.5 meters. The load is 200 newtons. And the load arm is 0.5 meters. So all we have to do next is isolate the effort. And you should be very familiar with this type of isolations, right? It's a very simple isolation. So it's this. And now all we have to do is calculate this expression. Let me do it very quickly with my calculator. And we get 22.2 newtons. So that's the effort that is necessary to raise that rock. And understand this. This is what you have to get away. Uh, Look at the effort. Look at how little it is compared to the real weight of the rock, which is 200 newtons. This is about 10 times less than the load than the weight of the load that you're trying to raise. So as you can see, the lever allows you to apply a very small force compared to the one that you're trying to raise. Okay, so that's why we use levers, because we want to apply tiny forces in order to lift heavy weights. Let's do another one. Example number 2, it's very similar to the one I already did. How much effort is it necessary to lift a bag of 100 kilograms of mass if such bag is placed 1 meter from the fulcrum of a first class lever of 5 meters? Again, let's draw very quickly the lever. So we have a bag in here. We know that the bag is placed 1 meter from the fulcrum, and we know that the whole lever is 5 meters in length, like so. Okay, so right away we can get, the effort arm. This is the effort. So the effort arm will be 4 meters according to the geometry, right? Very simple to understand. Okay, so let's write down my equation. No, let's first get the data like I did before. Let's have some consistency. So what is the data? What is my load? Don't write this as the load, because this isn't the load. Remember that I told you that a load is a weight, not a mass. So what you have to do is get the weight of this bag. And the weight is mass times gravity. So the weight, which I'm going to get it here, is the mass of the bag, which is 100 kilograms, times the acceleration of gravity, which is this much, as we know. And this is 980 newtons, right? So that's going to be the load. 980 newtons, fine. Now let's get the load arm, is 1 meter. And then the effort arm, which is 4 meters. And then let's find the effort. Now we write our main equation, the main equation of the lever, and we substitute. Like so, and we isolate the effort. So we will get this. So how much is this? Is in the end will be 245 newtons. Okay, again, it's much smaller than the real load. Look at this, that you're trying to lift. Okay, and let's do one more. I think it's also very closely related to the other two. So let's do it very quickly. You want to lift a bag of cement of 50 kilograms, which lays on the floor using a 6 meters long first class lever. The bag is placed 5 meters from the fulcrum. What effort will you have to apply? So again, this is going to take us under 2 or 3 minutes. Let's do it very quickly. Let me do it much bigger. When you draw in the problems in physics, I've been telling you to draw as big as you can. Don't be cheap, guys. You can don't draw tiny drawings, because if you do that, you're gonna cram all the numbers and all the stuff, and it's gonna be difficult to understand what you're doing. So draw as big as you can. Okay, so we have the bag of cement over here. We have the fulcrum. The bag is placed 5 meters from the fulcrum, so this is 5 meters. And now we know that the lever is 6 meters long. So all of this is 6 meters. Let me rewrite this number. Okay, so what's the effort R? Tell me, what is the effort R? This little bit, it's 1 meter, right? Okay, and also what is the load? The load will be the weight of the bag of cement. So the weight of that bag is its mass times 9.8. 9.8 meters per second squared, and that's going to be 490 newtons. So that's going to be my load. So let's come here with the data very quickly. The load is 490 newtons. The load arm is 5 meters. The effort arm is 1 meter, and I want to get the effort. So again, I write down my fundamental equation for the lever. And I get the effort, okay? So this is gonna be following, and then I substitute the load, which is, as we said, 490 newtons times the load arm, which is 5 meters, over the effort arm, which is 1 meter. So please calculate this in your calculator. And I get 2,450 newtons. That's what I get. And the reason I wrote this problem for you to solve, or for we to solve together, is the following. Look at what's happening here. Now the effort is much greater than the load that we're trying to raise. Can you see? So how come? What is the reason? The reason is that we are putting the load, the box, very far away from the fulcrum, and then we're applying the effort at a very short distance from the fulcrum. okay, which is not the case for the other two. In a moment, when we are done with this class, check out the other two diagrams for the example number 1 and 2. And you're going to notice that in those diagrams, the fulcrum is over here, and we have the load very close to the fulcrum, and the effort is far away from the fulcrum. But if you flip that arrangement, if now you do it this way, you're going to have to apply more effort than the load that you're trying to raise. Okay, so that may be seen as a disadvantage. But what do you think is going to be the advantage of doing this? What do you think is going to be the plus side of this? Huh? What do you think? If you're thinking of the following, you are going to be correct. The reason is the following: that if I do it, if I raise this box under this configuration, I'm going to have to apply a bigger effort than the load over a small distance, you see, but the box will rise a lot. Let me draw with blue. I hope it doesn't get so contaminated, the drawing. At the end, you're gonna have this, more or less, okay? I'm exaggerating, but you're gonna have this, and the box will be over here. So as you can see, the box will be raised a lot of distance, and you just apply your effort over a short distance. So that is the plus. You are exchanging distance for effort. You're gonna apply a lot of effort, okay, but you're gonna get out of this a lot of a lift, a lot of height of the box. So you see, so we can use the lever in order to raise to a greater height any object, as long as you put more effort than the load that you're trying to raise. Okay, so I hope you have understood these problems, guys. I believe they are simple. We have only one equation to handle, which is this, and it's a very simple equation. And that's it for me. And now we can pass to your activity. Thank you.